Yeah. I suppose no one has anything against the fact that we recorded lectures. Please tell me, or yeah, for example, if you speak, then your voice will be recorded also, but we won't spread it, so it will the recordings will only be for you. Lectures or schedule. So today, for example, do you see my schedule? Yeah. Today we'll have some math repetition, introduction to a program called Octave. It's just a mathematical software that one can use for doing calculations. Not necessarily the only one. It's quite similar to MATLAB, but a bit simpler. It's a freeware version of MATLAB, one can say. And then tomorrow, Ken will start with crystals and some crystallography. I continue on Wednesday with scattering, and Ken takes over on Thursday with point groups and such things. Afternoons will be devoted to, well, say, project or calculation exercises. These are the calculation exercises. They are chosen from a pamphlet called Lecture Notes. We don't have any literature or course book except the lecture notes that are available on the box or Dropbox area, and also here recommended literature is the International Tables for Crystallography, Volume A. Well, the 5th version came 2005. I think there is now Volume A is from 2016 or something like that. But essentially, it doesn't matter which version you have. There may be printing errors or different nomenclature in different versions, but I think you will have access to it. Those of you that are from Stockholm will have access to it from the university library. And for example, there are 2 of you from Uppsala. I think you should also have them available at your library. Otherwise, I suppose we can, if you have problems finding it, we can supply a PDF version on the area, file area. But this is not free, of course, but I mean, you can buy it also. There are in print, there is a brief teaching edition that is easy to carry around because it's just a pamphlet of 100 pages or so. The full book is quite heavy, like standard chemistry textbooks nowadays, but a lot more material. Maybe that is not necessary. You can ask your supervisor to buy it for you. Of course, that is a standard thing, standard reference work for crystallography. So costs something like 2,000–3,000 crowns or something like that. Otherwise, these calculation exercises, as I said, they are selected from the lecture notes. Some is just training for the training to do some calculations. It's not necessarily so that you need to hand in something, but there will be Eric and people on Wednesday. I will be there also. We will help you and guide you through calculations. If you don't have problems with doing these calculations, then it's essentially quite free time. But you're invited, and we're there for you. So project works. The first project will be looking in databases. This was maybe more important for some years ago, looking in databases and extracting structural information, and then drawing pictures. And we finish off on Friday with a short oral presentation. You select some project, for example, hydrated transition metal compounds, or something like that, and then you look in some databases. Now when we have it online, everything is online, by the way. We didn't plan anything on site, but except possibly later in the course where we have data collection, that is necessarily on site. So if you want to join us with some crystals, or we find you some crystals to deal with at a diffractometer, then you're welcome to Arrhenius lab. But that is beginning of February, yes. Until then, the idea is that everything is online. Mainly due to pandemic situation and corona and such things, but I think it could be done online with a calculation intensive course like this one. The blue parts of the schedule here is self-study time. Why is it blue here before lunch? That's because I have another course, so I can't be there. We have the lectures then in the afternoon. Lecture is F is Swedish föreläsning is a lecture, and L is lab. So it's not a big difference between a lecture and a lab, because all of them is theoretically oriented. And so if we do a structural solution by the interpretation of Patterson map as a lab, maybe we speak about it in very similar terms in the lecture the day before. Software. All of the software that we plan to use, except possibly some databases that are proprietary, that we can't give away. But most software should be freeware, or at least academic. For academic use, it should be free of cost at least. So the idea is that you download it and install it on your own computers. In Uppsala and Stockholm, you will probably have access to software at the departments, a lot of different software. So, but we can also guide you and suggest software to use. Yeah, and then the course finish by project 3, essentially. Then it's more or less 1.5 weeks or something like that. That there are two lectures, and then the project 3 is either on collected data or on some old diffraction data, that you solve a structure and perform all the different steps in the structure solution and calculations all the way up to, say, presenting it in a scientific article, or, well, we don't write an article, we make an oral presentation here, something like 15 minutes, so 10-15 minutes max. Well, we are nearly 10 people, I think, so 15 minutes will be a decent afternoon session. The times here are just given for guidance, but I suggest, is there no strong feelings that you should be free on Monday afternoon here, say some important game or something like that. There has been such request previous years that I managed to book something when there was an important football match or something like that. But then we can change it. Yeah, questions on schedule? No? Is that so? You're too kind. Then we should try to. Could you, by the way, can you access either the Dropbox or the box area?
Yes.
Yeah. One voice 4, yes.
Yes.
Yeah.
Yes.
Yeah.
I
So
haven't got any link yet, I think.
vad sa?
I have not received a link, I think.
And who are you?
Daniel HEDBO.
Daniel in Uppsala? Is that?
Yep.
Yeah, okay, yeah, that's you. I missed you actually because it's my fault. So I should send you the link. I haven't sent any links either to Dropbox or the box to you. Sorry for that, but I do that today. Anyone else with problems with the box or Dropbox area? Huh? Fine. Then please, Daniel, excuse me for forgetting you, but I'll send it after lunch or something like that. And then I will. Should I send out a list of participants with email addresses? Is that well? You will see that in the mails, by the way. So I should include you also. Now let's see lectures. Do you see lectures now? International tables, something?
Yes.
Yeah, fine. So, well, as I said, the only commercial course literature is this international tables, and if possible, if you buy it in print, you could actually buy it as the brief teaching edition. That's also quite cheap. It's 200 crowns or something like that. But I suppose you will have it available in an electronic version also. The teaching edition is not available as an electronic version, but the electronic version you have it. You have the full table. And also this so-called lecture notes. Sorry, what did I do now? Oh, no, for the course, it's just it's not a finished project, but there are some spread notes approximately in the same order as the content of the lectures. And the front page shows something similar to this. And I would say that this is approximately the idea of the course, to find the electron density at different positions in a crystal structure. What we experimentally is available is the intensities at different positions in something we call the reciprocal space, but we'll be back to that. We can measure a lot of intensity, scattered intensity, X-ray radiation, or neutron radiation, or electron radiation. It's approximately the same theory, and the crystallographic part of the theory is similar between any different scattering theory. But of course, the actual mechanism for scattering are different between X-rays and neutrons and electrons, even though they are similar in many respects. And the thing one can calculate from intensity is something that will be introduced as the Patterson function, or interatomic distances. That is quite easy, and it's a strict reliable calculations, but then we're stuck because we can't easily go from a Patterson. We will do that in a few cases, and that is at least an aim for the course to try to straighten out this question mark to exclamation mark, how to go from interatomic distances to atomic positions. On the other hand, if one would have some extra information here in the intensities, also something called the phase. So if we can attack the phase problem in crystallography in a reasonable way, we can find something called the structure factors that are in a way related to the intensities. If you know the structure factors, you can calculate the intensities, but unfortunately not easily the other way around. But having these, then it's just to calculate the electron density. So there are two problematic sides here that we will have a look at, and how to get around to go from intensities to structure factors, or via Patterson to electron density directly. One could also say how to solve a crystal structure. Yeah, find an automatic software and press the carriage return button, but that is hardly. Then we are finished with 7.5 HP already, but we don't gain any insight how to do it. Of course, one should use automatic software, and in very many respects, different type of well, simplifying procedures, but probably when you find an interesting problem, you will realize that the automatic software fails. So there is no way to get rid of actually struggling around with all of this theory, a little bit at least. Well, as I said, it's important that you do calculations. Try to do calculations really doesn't matter what type of calculations you do. Like some philosophers, they said that it's not important what you read, but the important thing is that you read. Western movies or something like that is as good as other more decent ones. Studying small groups is, of course, a good thing. You can perhaps, I mean, there are many of you at Arrhenius laboratory, so please feel free to join you together and ask for help or something like that. But otherwise, this is a problem with an online course like this. We help, but we don't necessarily check and grade calculation exercises. Computers. What kind of are you, I suppose many of you are using Windows?
Yes.
Yes.
Any
Yes.
Macintosh person?
That's very fancy.
It's very fancy, yes. So most of it, most software are available for Windows, and also part of it is available for Macintosh, but not everything. Same result is with Linux and such things, but yeah, Windows is quite reasonable. We will previously we have been introducing calculations a lot from software from command line, and we will introduce a graphical user interface this year for doing crystallographic information, but we'll see if that works. You can always do it via from the command line, and it's I'm so old, so I'm stuck with the command line. I started with the command line. I don't get rid of it. So and I don't want to, but of course it's very nice and very much more illustrative to have a graphical user interface. But we'll see when it comes to those points. The Octave program you can download from www.octave.org. There should be quite straightforward. With Windows, it's very straightforward. With Macintosh, it's slightly less straightforward, but anyway, quite easy. But you need to visit a storage area called GitHub, and there are information on a wiki at octave.org. So computer programs we will add up to the box area or Dropbox area. And databases, there says no databases here, but this is actually not correct. There is a free database available that is very quite large actually, and it's freely available. It's quite large. I said, meaning something like 20-30 gigabytes. So downloading it will be quite time consuming if you're not on a very fast line, but the speed could also be limited from the database side. But you can also search it on via internet. It's the COD, like torsk in Swedish, crystallography open database. Then one save the search results as CIF, crystallographic information file, and copy them to your own computer. Don't trust connections to internet sites that they should be stable, but if you produce some intermediate results, see to copy them to your own local computer or to some cloud area that you're trusting well. So editing input file, please don't try to use Word or something like that. In a simpler program, simple program available on Windows is Notepad, or there are other programs. One of them, my favorite editor is Emacs, but that is not available natively on Windows, but you can download it for Windows if you like. But Notepad is probably sufficient, or Write or something like that. So, to some math. What one a vector, I suppose you PhD students, most of you are PhD students or master students on some department here. So I mean, a vector is, depending on who you ask, is a set of quantities defined in a vector space, a mathematician would say. I hope none of you are mathematicians, or that's of course a good background actually for crystallography. But if you are, then please be a little bit forgiving with our handling of the nomenclature. Sometimes we use mathematical expressions that are not wrong, but maybe we are expressing ourselves slightly non-incorrect, so to say. In my view of a vector, we have something with the starting point and a direction and also a length and direction. Do you see when I write on the picture like this?
No.
No.
But we see pencil.
You see pencil only. Do you see it over here?
Yeah.
Aha, then I have a problem with, let's see. Do you see the red marking here?
No.
Uh-huh. Now then?
No.
Still not.
Shit. Sorry. Then wait. Yeah. Then I need to. Well, a definition. I see if I can use a blackboard later or a whiteboard. But obviously there is some problem with the drawing utilities in Zoom here. I could try to change a computer for next time. Definition, a typical vector is something that a quantity with the direction and a length, or say coordinates, a length along coordinate directions like along X and along Y. By the way, we can try this whiteboard. Do you see now that I write?
Yes.
Yeah, no problem.
Fine, excellent. Then we take a vector. A vector A, for example, could be expressed as say two coordinates, or I mean, where are the coordinates? It's if this is the endpoint, then if we assume that we start in the origin, then the X and Y would be there. And having two vectors, by the way, I usually denote with a bar on top here. This is not completely strict. Sometimes the bar means minus, and sometimes it means a vector. and the real meaning will, I hope, be obvious from the context. But in the book, for example, in very many books, you can have some quite bold character. This is a typical vector. Or in my writing with a bar, or maybe one should have a arrow on top of it. I don't know which one is the correct one, but in many in a lot of literature they use a bold case for vectors and non-bold for normal scalars. You can multiply vectors if you have a vector A, so you can have call it a multiply it with a vector B. That is essentially equivalent to a projection. If you have two vectors, if this is A and this is B, so then you can take the projection of this vector B on the vector A. Now B is shorter than A, but it could also be we can project A on B, and should be the same result. This could be said to be equivalent to the length of the different vectors times the angle in between here. If this is theta, then I think it is the cosine of, or is it the sine? Cosine? Let's see. If we fold it down, then it's 0. Cosine of 0 is 1, and sine of 0 is 0. So it should be cosine, yes. This is my way of arguing when I don't remember. I did remember actually, but I just want to illustrate that you should do some kind of arguing when you're not completely sure what you're saying. So this is a way to calculate the angle in between two vectors, or say that you have a carbon atom here and hydrogen, two hydrogens here, and then calculate these two vectors length, the length of them, and then you need to know this dot product. By the way, this is equally, if this is an orthonormal system that is with 90-degree angles everywhere, it's the AX BX plus AY BY. This can be said to be the actual dot product, because it's a dot here. With vectors, you also have another product. Strange in a way, but what's the difference between the dot product and the cross product? Or the one speaks about the vector product, because this is actually another vector with some interesting properties. It's perpendicular to both of these two, and it is actually a measure. The size of this vector is a measure of the area that is spanned, well, sort of area that is spanned by the two other vectors. So with the third vector product that is perpendicular to both of these, then we suddenly have a volume. This is convenient and helpful for dealing with the 3D space. So automatically we will, A and B do not necessarily need to be perpendicular to each other, but C is perpendicular to both of them. So we have sort of volume element. This is also the length of one vector times the other vector times the sine of the angle in between the two vectors. Same as we definition as we had here. It's the other trigonometric version. If the angle is 90 degrees, then sinus of it is 1. So then it's just a rectangle. That seems to be okay. If the angle is 0, sinus of 0 is 0. So if the area that is spanned of two collinear vectors is of course 0. This seems to be correct, yes. How to calculate this vector? Yeah, you can set up a determinant with a 3 by 3 determinant. So AX, AY, AZ, BX, BY, BZ, and then these EX, EY, EZ could be the unit vectors in the XYZ directions. This is described in the lecture notes, how to do it in practice. Let's see if I forgot something. Dot product, vector product, and by the way, right hand rule, it says here. This is very important. Why should we have bother about describing things in right-handed coordinate system? It's a good question, but it's a negotiation in a way. So let's we don't want to come into the situation that I speak about the crystal structure like my right hand. This is my right hand that I'm holding up now. And you end up in describing a left hand just because you forgot to mention that you are looking in a mirror or something like that. One could perhaps think that that should be of no practical interest, but it is. Some chemicals and some drugs, for example, are poisonous in the left-hand side while they are healthy in the right-hand side, or vice versa. It could be very important to have, it is very important to know the so-called absolute configuration of different compounds. And everything should be described as in a right-handed coordinate system. Where the thumb is the x-axis, the pointing finger is the y, and this finger is the z direction. So then you can see physicists, for example, they are looking at rotations with the hands like that. That is quite convenient. With vectors, you have Cartesian, that is, you give the parts, the XYZ parts, or vectors do not necessarily need to be 3-dimensional, it could be any dimensional, as many dimensions as you wish, but it's difficult to visualize with more than 3 dimensions. Or you can make it a polar representation. In 2D, it's just the length and the angle to, say, the x-axis or something like that. In 3D, you need 2 angles and a length. And in 4D, 3 angles and a length, etc. But while it's used in 2D and 3D very commonly, But maybe we will see it mostly in 2D when we represent this structure factor as a vector in a 2D plane, in a 2D complex plane in a way, but it's just slightly different way of visualizing a structure factor. Determinants is something you calculate from an arrangement of a matrix that I showed you in the previous pictures. There is a real space unit cell, real space representation of crystal structures. Reality is real, so that is probably you can hear it on the word reality. It's not so complicated, but in a vector, you can't divide vectors, but you can. Hoppsan! No, my pen was crazy. Now let's see. Clear all drawings. Nej, det gick inte. We'll see. Whiteboard, yes. So, if you have a vector A, you can't divide it by a vector B. That is not a defined operation. But I mean, if you take a vector A and multiply it with another vector B, then you won't get the same result. But if we define a reciprocal version of the vector B, then we can sign that this should be unity, or the unit vector. No. Like that. And then one can sort of that's a way to have something similar to division, even though it is not division. So if you have a space A, B, C, there will be another space, A star, that is perpendicular to C and B star that is perpendicular to A and C, and C star. This is convenient, a convenient construction for dealing with diffraction space later. The reciprocal space construction is just a construction dependent on how the real space look like, with some extra details, that A star is perpendicular to B and also perpendicular to C, but you can't say anything. A star and A, there is an angle in between, but that is not necessarily easily known. Yeah, that is essentially the length of A. What do I say here? I mean, yeah. Sorry, I'm a bit fussy. This is the result, but this is equal to A times, and not necessarily unity. So Now let's see. Time runs. Clock is. We come to matrices. Clock is 10:49. Should we make a short break to 11 o'clock or something like that? Have some coffee or something? Are you
It's
there?
all the same. Yeah, for me,
Yeah.
it's all the same.